Video, we're going to discuss peak widths. As we said, a peak in a diffraction pattern we can think of as having position, width, and some sort of intensity. So what are the factors that are going to affect the peak width that we observe? Well, the first factor that we might want to consider, which is related to the actual sample itself, is the crystallite size. If we go back and think about our example of Young's double slit in diffraction there, what we said is that if we have two slits, we produce a diffraction pattern. If we then add a third slit to it, and then a fourth slit and a fifth slit, and so on and so forth, what we get is we get that combined interference, and our diffraction pattern gets sharper, and our peaks get sharper and sharper still. We can think of the same thing happening with the crystallite size. As we add more planes of atoms to the structure, we're effectively increasing the number of diffraction slits that we have in our experiments, the number of planes contributing to that diffraction interference. And so as we increase the number of planes in our structure, we're going to make those diffraction peaks sharper and sharper and sharper. Another way of saying this is as we increase the crystallite size, and therefore the number of planes, our diffraction peaks will be observed to increase in sharpness, i.e. the width will decrease. So what we can see here on the screen is an example of how if we go from a very small crystallite to a very large crystallite, what we see is we get gradual narrowing of those peaks. So in the bottom right, we've got a very small crystallite, only 10 nanometers, and we've got very broad diffraction peaks. Whereas in the top left, we've got very large crystallites on the scale of 10 microns, and now we've got very sharp diffraction peaks. And actually, we can model this with what's called the Schur equation, shown here on the left-hand side, where what we've got here is this beta value is showing the peak width, and we can see that it's inversely proportional to L, which is the crystallite size of our material. So if L gets larger, beta, the peak width, will therefore get smaller. Now there's a derivation of this in the notes if you want to see the derivation of how we get to the Schur equation. So we can see that the crystallite size will therefore affect the peak widths. Another key factor that affects the peak widths from the sample is the microstrain within the system. So depending on the crystal that you're studying, this may or may not be important. For example, if you're studying metallic systems, the microstrain, the dislocation density within the material, is going to be very important. So we've got here a picture of dislocations within the material. And what you can hopefully see is that when we've got a dislocation in the material, what we're getting is we're getting a disruption of the interplanar spacing within the material. Rather than having one well-defined interplanar spacing, because of that dislocation, we in fact see lots of different dislocations, despacings within the material caused by that dislocation. The consequence is that we can think of it as basically, rather than just having one peak at a single despacing, essentially what we've got is a whole load of overlapping peaks, all of which are at slightly different despacings, caused by the fact that we've got a variation in this interplanar spacing here. The consequence when we sum all those together is effectively that our peak appears to broaden out. So we get an increase in breadth of our peak if we have lots of dislocations within the material. And again, we can model this by this equation here, and we can see that what we've got is a change in width that corresponds to the dislocation density given by this value epsilon here. So we can see that we can relate these two together. So if we have a variation in the dislocations, we will get a variation in the peak width. One thing that it might be worth noting at this point is just noting that this variation with microstrain varies as a function of tan theta. So depending on where in the diffraction pattern, where in theta we're observing our peak, we'll see a different amount of broadening based depending on the microstrain. This is different compared to the crystallite size, where we have a 1 over cos theta dependence, a sec theta dependence. So actually, depending on whether you have crystallite size broadening or microstrain broadening, you'll see a different observation at different points into theta, different amounts of peak broadening. And this allows us therefore mathematically to separate out these things. So we can tell the difference between whether the broadening in our peaks is coming from the crystallite size or the microstrain broadening by considering how different peaks across our 2 theta range are broadened by different amounts based on these two effects. Now, as well as sample-dependent broadening, we'll also have broadening that's caused by the instrument itself. As we discussed previously, our peak shape we can think of very often as something like a pseudo-void, where we've got a Gaussian component and a Lorentzian component. And as a first approximation, very often what we can say is that these microstrain and crystallite size terms, the terms that are related to the sample, control the Lorentzian. Now, in more complicated circumstances, that may not strictly be true, but as a first approximation, often we find that they control the Lorentzian term within the peak width. When it comes to instrumental terms, depending on the optics that we've used and the setup of our instrument, we'll get some sort of peak broadening caused by that setup. For example, if we change the divergence of the beam, we would expect the peak shape and the peak width to be affected by that. And actually, this tends to affect both the Gaussian and the Lorentzian terms within our pseudo-void. And very often what we do is we model this by a certain equation called the Cagliostro function. And this is shown here on the right-hand side. So this, we can see sigma squared here is our Gaussian peak width. And we model this by this equation u tan squared theta plus v tan theta plus w. So this is our Cagliostro function that's controlling the peak widths as a function of theta. So based on where they appear in theta, we may have different peak broadenings caused by the instrumental function, and we're going to capture that with this Cagliostro function here. And similarly, we have another term that is the Lorentzian term here caused by the instrument, where we have x over cos theta plus y tan theta plus z here. And so what we'll generally do is, in order to get these, is we'll fit a known material with these functions. So we'll do a refinement where we have a known material, something like lanthanum hexaboride, where we know the crystallite size and microstrain that we expect to get. And so we can fix those terms for the peak width and just refine the instrumental terms that we see here. And so get good values for u, v, w, x, y, and z for our instrument. What we can then do is go over to our sample that we're trying to measure, and we can therefore keep those instrumental parameters fixed, our u, v, w, x, y, and z, and just refine the parameters that are related to the sample related terms, so the microstrain and the crystallite size broadening. So this is really important to understand, is that we have these two effects, the instrumental effects and the sample effects. And what we hope to do when setting up our refinement is set up with a good instrument parameter file which captures these u, v, w, x, y, and z terms within it. And as I say, those terms we can capture by refining a standard, a known standard, and getting good values for those terms. If we don't have a good instrument parameter file when we're doing our setup, what that means is we might be able to refine, still get a good refinement and still get a good image of, or a good fit to our data. However, if we don't know those u, v, w, x, y, and z terms, we can't then be confident about the crystallite size and microstrain broadening terms that we refine and get out at the end of refinement. We might just have to combine it all in the refinement in terms of the instrument parameters. So this is where it's really important to understand what our instrument parameters are, what our sample parameters are, and which ones we need to refine in order to get a good fit. Just coming back previously to some of the comments I made about microstrain broadening, microstrain is going to be particularly important where we have dislocations in our material. So when we've got things like a metallic system where we're likely to have dislocations. Depending on the system that you're looking at, this may or may not be important. So it may or may not be sensible to refine the microstrain during a refinement based on your sample. So it's important to understand whether or not these parameters are going to be important within your sample and choose whether or not it is important to include them within the refinement suite. But overall, if we look at our table, we can think of our peak width as being related to some of these things, our crystallite size, our microstrain, and our peak width parameters that come from our diffractometer, so our instrument parameters there. So if we're doing our refinement and we're not getting the peak widths quite right, then we'll want to consider refining one or more of these. And then we're going to have to go through the usual decision of which one of these we're going to refine and in which order.